Hello everyone. Um, I'm gonna start chapter 5, section 7, rotating frames. So far in all the problems that we had, we were dealing with just inertial frames. It means our x direction and y direction, they were certain directions. Usually we had, for example, x direction as horizontal direction and y direction as vertical direction or something like that. But they were not changing x and y, they were fixed to the ground. But sometimes that's not the case. For example, just consider an airplane. So let's say we have something like this, an airplane. Looks like a bird, but imagine this is an airplane. And you have a sensor here to observe other airplanes or other flying objects. And let's say we have this flying object here, right? It is moving and going around, and you want to track that with that sensor. So the sensor, which is fixed on the body or inside this airplane, is tracking this. But the sensor itself is going and rotating around with this airplane. And the sensor doesn't have any idea about its movement or rotation of it, right? Let's say this object is fixed at some point. It's not even moving. And this airplane is just rotating around. Then the sensor is gonna see this object is moving around, which is not correct, right? The actual velocity and position and acceleration of this object is totally different than what the sensor is observing. So to make this a little bit more abstract and more mathematical, let me start with this. Let's say we have a coordinate which is fixed to the ground. It is not moving. I'm gonna call x of it capital X, and the unit vector of it, I'm gonna show it with capital I hat. And the y direction, I'm gonna show the unit vector with capital J hat. And let's say we have another coordinate. I can show it with a different color. Another orthogonal coordinate. Let's say this is x and this is y. Small I and small y. And the unit vector here is I hat and also j hat, small I and small j hat. Now, let's say we have a point here, which is moving around, and I'm showing the location of this particle with this vector r. So we have this vector r. You can show this r in terms of small I and j hat, but you can show the same vector with the capital I j hat. Both of them are showing the same point, right? But you can actually write this vector in any coordinate you want. In this coordinate, you are gonna have a different number for I and j, but if you use this coordinate, you are gonna have a totally different numbers for x direction and y direction, for I hat and j hat direction, right? So let's say we are showing r in terms of small I and small j. So r is equal to x times small I hat and y times small j hat. Okay. Now, if I want to take a derivative of this vector to find the velocity, the actual velocity of this point, let's call it p. Let's see what happens. So velocity of p, or dr dt, is going to be equal to derivative of the other part, right? But derivative of x is going to be something like x hat, x dot times I hat plus y dot times j hat. But I and j, they are not constants. So the derivative of this I hat, j hat, they are not equal to 0, because I guess I forgot to mention this. This coordinate, this small ij coordinate, let's say it is rotating with angular velocity of omega. It is not fixed to the ground like the other one. The other one is fixed to the ground. So because it is rotating, the orientation of a small I hat and a small j hat is not going to be fixed. It's not constant. So they have derivative, right? So I'm gonna have plus x times derivative of I hat with respect to the time, which is not equal to 0 here, because as I said, I hat is changing with time. And same thing for the other one, y times derivative of j hat times over dt. What is di dt and dj dt? I didn't prove this, and I'm not going to prove it here, but the proof is quite simple. You can take a look at the book, your book, to find it out. But derivative of any unit vector, like for example I hat, with respect to time, is going to be the angular velocity of it cross the unit vector. We can prove this, but for now, just accept it from me. So same thing for j hat. Derivative of j hat with respect to time is going to be omega cross product to the vector j hat. So if I replace this in this equation, then see what happens. Derivative of with respect to time is going to be x dot plus y dot in x dot I plus y dot j. Plus x times omega cross I and y times omega cross j. So I can take the omega out and write it as omega cross product to xi hat plus y j hat. And this is nothing but r. And what is this? X dot I plus y dot j. If you sit on this coordinate and rotate with the coordinate yourself and look at this point P, then the velocity of P in your eyes, which you are rotating with this coordinate, is going to be x dot in the I direction and y dot in the j direction. So this is the velocity of that particle in this coordinate. Again, if you sit on this coordinate and rotate with the coordinate, and let's say you don't know you are rotating and you are looking at this particle, this is going to be the velocity that you are seeing about this particle. So I'm going to call this, you can call it dr dt in the second coordinate, or in this course we call it the relative velocity of that particle in the rotating coordinate, and show it with v rel. So what's the meaning of that all together? The actual velocity of the particle is going to be the relative velocity of the particle in that coordinate plus omega cross r. Omega cross r in that coordinate. Okay? So this is the way to find the actual velocity of P. I need to know what is the velocity of this particle in this coordinate. Again, if you sit on this coordinate and rotate with the coordinate and look at this point, that's going to be the velocity you are seeing, right? But that's not going to be the actual velocity. You need to add this term to it too, omega of the coordinate cross r. Now let's make it more complicated even, and let's say this this coordinate is moving around too. It is moving and also rotating all together. So let's say we have a coordinate fixed to the ground. I'm going to show it with capital X and capital I hat, capital V and capital J hat, Y and J hat. We have a coordinate here which is rotating with angular velocity of omega, and also the origin of it is moving around too. I'm going to call the origin of it B, or show it with B. And like the previous problem, I'm going to show the unit vectors with small j and small I and small j hat. And let's say again we have a point here which is moving around. I'm going to show the location of this particle in the moving coordinate, in the rotating coordinate with r. But this r is not the actual location of P with respect to the ground. The actual location of this point is a vector from the origin of inertial coordinate, which is fixed to the ground, to the point. I'm going to show that with RP. And also I'm going to show the origin of this frame, the moving frame, the rotating frame with RB. So what's going on? The actual location of this particle, RP, is equal to RB plus R. Okay. Now, to find the actual velocity of this particle, I need to take a derivative of this equation with respect to time. Derivative of RP means the actual velocity of this point. So derivative of RP with respect to time is going to be VP, the actual velocity of this point, is equal to derivative of RB means the velocity of point B, velocity of B, plus derivative of R. R is a vector in this coordinate. So taking derivative of it, we have to actually do similar to what we did in the previous one. Derivative of R is going to be omega cross R plus the relative velocity. So it has two terms. That's the point of this section. So the actual velocity of P is going to be the velocity of the origin of the moving coordinate plus omega cross R plus relative velocity. This is the equation that you need to learn to solve the problems for this section, the velocity problems. So sometimes, again, just to recap it, sometimes we have a moving coordinate which is moving and rotating, and let's say you have a point which you are showing that point with a vector in that moving coordinate. To find the actual velocity of that point, you need to find you need to know relative velocity of this point in the moving coordinate, VREL, then add the velocity of the origin of the coordinate and add omega cross R. Omega is the actual is the rotational velocity, the angular velocity of the coordinate, and R again is the location of point P in the moving coordinate. I'm going to solve a few problems using this and then extend this to acceleration, how we can find the acceleration of this point if we show that point in a moving and rotating coordinate. The acceleration is going to be a little bit more complicated.